Welcome to the Basic Physics Laboratory. This time, we will study the practical material entitled Uniform Accelerated Linear Motion, Uniform Linear Motion, and Pauli inertia moment. In this material, we will divide it into several outlines. We will study it starting from the objectives, basic theory, tools used, experiment procedures, and data processing. First of all, we will see from the objective of the experiment first. So the objectives of the experiment in this material, there are three, namely, learn about uniform accelerated linear motion using Atwood machine, learn about uniform linear motion using Atwood machine, and determine Pauli inertia moment Atwood machine. Maybe all of you are still confused about what is an Atwood machine. Don't worry, because later we will describe what an Atwood machine is. Next, we will study the basic theory. The first basic theory regarding uniform accelerated linear motion. So, uniform accelerated linear motion is a motion that occurs on an object while moving in straight line. Accelerated linear motion has constant acceleration value against time. So it can be concluded that in uniform accelerated linear motion, the values of initial velocity and the final velocity are different because of the constant acceleration. In uniform accelerated linear motion, there are three equations. The first one is st equals to so plus vo times t plus half a plus t square. The second one, vt square equals to vo square plus 2a times s. And the last one, Vt equals to Vo plus a times t. With sts, final distance in meter, so as initial distance in meter 2, Vo as initial velocity in meter per second, Vt as final velocity in meter per second 2, a as acceleration in meter per second square, and t as times in second. In the uniform accelerated linear motion, there are four graphs. The first one is distance time graph. In distance time graph, we can see that the graph is forming an upward curve. This is because the s value is directly proportional to the square of time so that it forms an upward curve. Right next to it is acceleration time graph. In acceleration time graph, it's formed a horizontal line because the acceleration value doesn't change with time. And the others two are velocity time graphs. We can see that the velocity increases constantly with time. This is due to the acceleration value that doesn't change. The difference between the two graphs is that one of them has the value of Vo or initial velocity, which means that the object doesn't start from rest but is already in a state of motion which is then accelerated. In the uniform accelerated linear motion, there are two applicable laws, namely Newton's second law that can be formulated with equation sigma f equals to m times a, and Newton's third law which states that f actions equal to f reaction but have opposite direction. And now, the basic theory of uniform linear motion. Uniform linear motion is motion that occurs in one dimension of space at a constant speed and direction. In contrast to uniform accelerated linear motion which has constant acceleration, in uniform linear motion which has a constant value is the velocity. So, the equations are also different. In uniform linear motion, there is only one equation, and that equation is st equals to so plus v times t, with st as final distance in meter, so as initial distance in meters 2, v as velocity in meter per second, and t as times in second. Uniform linear motion only have two graphs. The first one is position time graph. In position time graph, the s value increases constantly with time. And the other one is velocity time graph. In velocity time graph, it's formed a horizontal line. Both of those things happen because the value of the velocity is constant. In uniform linear motions, the only applicable law is Newton's first law, which states that sigma F equals to 0, or the resultant forces equals to 0. The last one is basic theory of Pauli inertia moment. The moment of inertia is a measure of the inertia of an object rotated on its axis. Inertia of an object to a particular axis in proportion to the mass of the object and is proportional to the square of the distance of the object to the shaft. Right here, we will learn how to measure the inertia moment of the pulley from Atwood machine. Then, the equation of inertia moment is I equals to m times r square, with I as inertia moment, m as mass, and r as radius. And right below it, there is an acceleration equation which states A equals to m3 times g over m1 plus m2 plus m3 plus I over r square. We will learn this acceleration equation on the next experiments video. And the last are the tools we will use. The tools that we gonna need for uniform accelerated linear motion are a full set of Atwood machine that consists of scalar pull, pulley and rope, 2 loads M1 and M2, 2 extra load M3 and M4, clamp, hole holder, and base. We also need a vernier caliper to measure the pulley radius, stopwatch to record the load movement time, and a house triple beam balance to measure the mass of the load. In the picture given seems to lack that there is no scalar pull. If described, the scalar pull is a pull that supports the pulley and has a scale to calculate the distance of the load movement. The tools used for uniform linear motion are not much different from uniform accelerated linear motion. We need a full set of Atwood machine and a stopwatch. For pulley inertia moment, we only need vernier caliper to measure the pulley radius and a house triple beam balance to measure the pulley mass.
Welcome to Physics Laboratory. Right now, we will learn uniform accelerated linear motions and uniform linear motions. Before we begin, firstly, we will look at the tools that we use in this practicum. First is the Atwood machine, which this tool we will use to observe the uniform accelerated linear motions and uniform linear motions. Atwood machine is connected to the timer, which is to record the time for the attempt. Hereinafter, we have the house triple beam balance that we will use for measuring the mass of 2 extra loads and also the main loads. The loads we will install on the Atwood machine. Next, there is a vernier caliper to measure the diameter of the Atwood machine pulley. Therefore, we can calculate the value of the moment of inertia. After we know the name of the tools, let's measure the load on the Atwood machine, and also the extra load of the Atwood machine. Here we will measure the main load using the Ahaus balance. For your information, the Ahaus balance has the smallest scale on the value at 0.01 gram that you can look directly on that. So we can know that the uncertainty of this Ahaus balance is about half times of the smallest scale. It is 0.005 gram. When we measure the main load, let's put the load in the pan. Then we slide the beams until the load is balanced with the beam. Here we got the data of the load mass, it's about 101 grams. After that, we will return the beam to its original position. Then we continue to measure the extra load. With the same way as the previous method, by balancing the load and the beam. Finally, it is nailed on zero position. So we know that the mass of the extra load is 5 grams. After measuring the mass of the main loads and extra load, next we will measure the diameter of the pulley using a vernier caliper. As we know that the calipers is divided into two scales, namely the main scale and the non-year scale. The smallest scale value of the calipers in here it is 0.02 millimeters. Then we measure the pulley with the calipers. Then we lock the screw. After that, we have to see that the lines on the non-year scale must be the same as the lines on the main scale. Or by saying where is the lines that are exactly parallel between the non-year scale and the main scale. In this case, we see that the measure result is nailed on 13 centimeters. As we see, the number 1 in non-year scale is parallel to the fifth line. Therefore, we just need to multiply the non-year scale we got with 0.02 plus the main scale, and it is for the final measurement result. After this, we will take data of linear motion. The following is how to operate the Atwood machine. First, for the uniform accelerated linear motion, we will measure the time when the load falls from the point A to the point B as the endpoint. Using the timing controller, our first attempt will try to drop the load with one extra load on the distance of 10 centimeters. Then, the second try uses one extra load with a height of 15 centimeters. Then, we drop one extra load at height of 20 centimeters. And finally, we will drop one extra load from a height of 25 centimeters. After we use one additional load, we will adding some extra weight, with the same weight to the previous experiment, with a height of 10, 15, 20, and 25. Now we will try with a height of 10 centimeters using 2 extra weight. In the second experiment, we will use 2 extra loads at a height of 15 centimeters. Then, we will drop 2 extra weight at the height of 20 centimeters. And finally, we will drop from a height of 25 centimeters using 2 extra load. And the next is uniform linear motion. We will drop this load and we will start to record the time when the extra load is stuck on the holder. And the final time is when the load lands on the base. This time, we will drop the load from a height of 10 centimeters. Then, we will increase the height to 15 centimeters. Then, we continue at a height of 20 centimeters. And finally, we will drop the load at a height of 25 centimeters. The last part is the moment of inertia. We will find out the moment of inertia in the system by finding the inertia value of the pulley from the data of the radius that previously we measured using the caliper, and also the data of all the loads. And finally, we just have to calculate it with the formula.